Okay, we're going to walk through in this video how to use some of these equations that we're seeing in the Wildlife Ecology and Conservation textbook to generate something like these curves. So there's a lot of figures in this book that are explained by equations. These equations are meant to present models for prediction. And a lot of what we're seeing here is how actual data will fit a model of prediction. And so the first one from chapter 10 is a function here that is predicting an energy gain, okay, based on a few different variables. Okay, and so let's walk through some of these variables. E, which is the energy content of that food item. Okay, let's say this is the optimal food item. This is the curve for the optimal food item with the highest energy gain compared to its energy expenditure for getting it. Okay, so E is the energy. Correct that spelling there. A is the area searched. N is the population density, the density of the item. Okay. And then H is called handling time. And so this function can be drawn when you see changes in any of these variables, whether it be the energy content or the area searched or the density of the food item. You can plug this in and make a predictive curve based on those shifts and changes. A lot of what we were talking about was, let's think about an optimal food item. So let's just envision it's a single type of item, it is of a set size, and it's considered the optimal food item. And so we're going to plug some numbers into that scenario, and all we're going to be changing with the scenario is how dense, how frequently you would find that in the area that you would be searching. Okay, so we're going to build a data set in Excel. So in the process, you may become more familiar with Excel, and then plot a curve. See if we can use this exact function here to plot a curve that's similar to the one here in the textbook. So I'm just going to move this graph over here, and I'm going to move the predictive function equation over here, and then we will, maybe in another video, move on to this equation that's comparing when you would be a generalist, when it might be favored to be a generalist versus a specialist. So let's create some scenarios, and I'm just going to number them. We'll create 10 scenarios here. So and our hypothetical food item, these equations aren't defining terms in terms of what are the units that we're using, and I'm not going to either, but you can think of energy as kilojoules or kilocalories, that energy content in the food item, and let's just say that is 10. Okay, the area searched, again, we're not defining units here, but let's use the metric system and say it's hectares. So 1 hectare is being searched. And then the density, let's make this food item, at least at the beginning, not very common at all. So if you search a hectare, you may not even find one. You might have to search 10 hectares to find one. It's really rare. So 0.1 per hectare. And then the handling time, I would assume this would be seconds or minutes or something like this. Let's make it 4. Okay, so those are the variables in the equation. And what I'm doing here, I'm not taking any real data set. I'm simply plugging some numbers in to see how this equation works. If I start to think of some hypothetical example of a food item, to see if I can draw this function. And so one thing you can do in Excel is you can enter in this entire equation. And so what you would do is you would type in an equal sign and you would enter in the terms for this equation. And it could calculate the equation with these variables here in the different columns. I like to do my equation in pieces because it helps me to track problems. If I make some error in the symbology that I use or in something that I type, if I've broken it up into pieces, it makes it easier for me. If you prefer to type the whole equation into one cell, that's fine too. So we're going to start off though with typing in the equation that represents this part, the energy the area searched, and the density. And so we're multiplying all of those variables. And so we do that with cell referencing. So the first thing I do, I tell Excel that we're about to do a formula. And so I type in the equal sign, and then I use cell referencing. I don't enter in my numbers. I select the cells with the numbers, and that's going to make it easier when I want to apply this to more rows of data. So I'm going to click this cell because that represents the energy content of my item. And then asterisk is your multiplication symbol in Excel. I'm going to multiply that by the area searched, which is here. And then I'm going to multiply it again by the density of that item in the area. So that represents the top part of this equation. Okay, make sure I did that right. Yes, okay. Now the bottom part of the equation, I'm going to start again with an equal sign. I type in the number 1, and then plus, and then I use parentheses quite a lot in Excel just to make sure that I'm doing order of operations correctly. And so the natural order of operations is that multiplication happens before addition, I believe, but I always put in parentheses to make sure. So you want to have these numbers multiplied first before adding the 1. Okay, and so you're going to have area times handling time times the density. Okay, so that is the bottom part of my equation. And then the final piece to make the actual output, the correct number for this row of data, I'm going to type again, equal sign again. I'm going to take the top and divide it by backslash the bottom. And there is my resulting number. So if I were to put this on a graph, it would just look like a 0.714, etc. This function only really has meaning if we're changing something. A function is something that's representing change. And so what I'm doing here is because of the content of what we're talking about in the text, we were talking about how changes in the availability of an optimal food item can influence consumption of that food item. So I'm going to keep, and I'm going to add some scenarios here. I'm going to keep the energy content, the areas searched, and the handling time the same for these food items, but I'm going to be changing how frequently those food items are encountered in the environment. And so I'm going to start off by trying 10 scenarios, and I can type these in. I'm actually going to use this. If you type a few numbers in that are sequential in Excel, you can actually use this drag option. And so once you see the square show up in the corner here, you can drag down, and it will automatically increase by one increment, one integer in number until you get to what you want. So we're going to do 10 scenarios. And in all of these scenarios, I'm copying this cell and pasting. The food item has the same caloric or the energy value, okay? And in all of these scenarios, the area being searched is the same size, okay? Also, per food item, the handling time is the same. The only thing we're manipulating here or changing is how available it is, how densely populated it is. So I'm just going to increase it by increments of tenths. And let's see if it will do that. Yes, it will do this for us here in Excel. Okay, and so now we're looking at these differences in abundance of the food item. And because I've used cell referencing for all of these formulas here, I can do something really nifty. I double check that I've entered these equations in correctly for the top, the bottom, and the total equation, and it looks like I have. So I'm actually going to select all 3 of these cells. And again, when this little square box pops up, I can then drag. And because I've used cell referencing, Excel will actually put that same exact equation, but assume that I am looking at this row of data now. So you can actually double check that. So instead of typing in these numbers, it's saying the formula that Allison entered is equals B2. So this is cell B2 right here, times C2 times D2. But in this one down here, this next row, it's cell B3 times C3 times D3. And the same should be applying to these. And so we have correctly entered that formula once, and now we can drag it down and apply it to a whole data set. And so now we have this data. And what I want to do is to plot, see if I can make a plot like this one. I'm going to see if I can drag it here so we can look at it again. And so I need to know what my X and Y axis is. So for this example from the textbook, the X axis is prey density. So that's your N variable. And then the energy gain is this output here. Okay, the function of the energy gain is this number here. Okay, because the energy gain is not the total energy, it's the energy times the area searched times the density of the object divided by the handling time, the area searched, and the density of the object. So that's your energy gain. So for each row, we have this calculation right here for energy gain. And so that's the function of energy gain. So I want to plot these values here as my X, and these values here as my Y values. And so to do that, it's a lot easier in Excel to do it if you can put those two items side by side with one column, the X set of values to the left of the Y set of values. You can do it without having them right next to each other, but I'm going to put them together so that it's easy to do. And so all I'm going to do here is I'm going to copy this row and I'm going to insert it. And I just have to make sure that when I do that, that the formula stays correct. So I look at these numbers. Yes. And again, I can do that by looking to see if it's dividing the right two numbers together. Yes, and it is. So this is going to be my X, this is going to be my Y. And so what I do here is I'm going to select these two columns of data, and I'm going to say insert. I'm going to select the menu for insert up here in Excel, and I'm going to select scatter plot. Okay, insert a scatter plot. And I just want to insert a simple scatter plot. Scatter plots are one of my favorite plots. In Excel, if you have two variables, you want to see how they relate to each other, that's the kind of plot you want to do. And so you can see that we have generated a plot that actually really looks a lot like this one. Now it looks a little more stretched out. I can actually fit a line. I don't want to add a trend line. I can actually go into this plot and add some lines. Let's see if I can do that. I can do that through the formatting of the chart. So you can add the trend line in a variety of ways. One way is you can actually connect the dots. When you first select your type of chart, you can have it be a scatter plot with the lines with the dots connected. Here, I'm going to actually add a trend line because it looks like a logarithmic trend line. And when I click that, it puts in a regular line, but I'm going to ask for logarithmic here. I'm going to select that. Okay. And the only thing that it's not showing me here is it's not connecting that line down to the bottom. Okay. But this line would connect right down. And so we have some different options we can use to make that happen. Now you may also be noticing that my line, or the line that we generated with this data set, looks flatter, but it's also important to note that the way that the X and the Y axis are stretched out on this graph is basically in a square, and compared to this one that looks much more rectangular. So you can simply reshape your chart to be much more square shaped if you really are wanting to compare what it looks like to this illustration here. And now it looks really similar. The numbers, the scale, because the numbers I entered are different, but this function looks almost exactly the same. So it's these equations that are provided in the text are meant to be presenting you with the actual models that the researchers use to make these predictions. And so say that I'm predicting some sort of optimal foraging, and I'm manipulating the availability, or we go into a natural environment where there's some gradient of the availability of the most optimal food item in there. And we make observations of the feeding behavior of something. Well, you can plot this function as the prediction. If the animal is acting optimally for energy gain in its environment, you can actually collect information on how frequently it's choosing this food item, and given the density of it in the environment. And then you can plot that data, your data, compared to the model. And then you can do something like a regression or a model fitting analysis to see how well your own observations meet this prediction. And it's a pretty simple prediction, and it is that as the favorite food increases, consumption and energy gain increases, but beyond a certain point, there's so much of that food in the environment that you're limited now by the amount of time that you have to actually process it and handle it and digest it. So pretty straightforward prediction. Looks like complicated math, but it's really meant as a starting point for testing a model, a simple model. And we'll cover this slightly more complex model in another video.